Picture this. You are deep in the trenches of your very first major machine learning project.
Oh yeah, we've all been there.
Right. You are running this massive hyperparameter search for a neural network, just diligently testing out different layer sizes, learning rates, the works.
Sounds like a solid Friday night.
Exactly. So you have 10 different experiments lined up. You kick off the runs, step away from the terminal, and maybe, just maybe, actually get some sleep.
If you're lucky.
Yeah, big if. But the next morning, you check your login dashboard, and the results look phenomenal. Like, better than phenomenal, actually.
Uh-oh, that's usually the first red flag.
It really is,
Yeah.
because as you dig into the underlying data, your stomach completely drops. You discover a total disaster. Experiment 1, the run you thought gave you this massive breakthrough, actually ran with the hyperparameter settings from experiment 10. Yeah, your base configuration was silently mutating across the runs in the background. And the culprit. You used a simple, shallow copy on a nested dictionary structure. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
That scenario, it is the ultimate invisible trap for anyone moving from like standard Python scripting into actual system-level machine learning.
It's terrifying because there's no error messages.
Exactly. You put in the work, your syntax is totally flawless, the compiler doesn't throw a single warning, but your underlying logic is compromised from the very first evoc.
Wow.
In the industry, we call this experiment contamination. And it is a total nightmare to debug, specifically because, like you said, there was no glaring red text on your screen telling you what went wrong. The system just, it fails silently.
Which is exactly why we are dedicating our entire focus today to bridging that specific gap. We are taking you from knowing basic Python to actually building reliable, bulletproof machine learning systems.
Yes, because today is all about copying strategies, memory-safe design, and really developing the engineering mental models you need to stop these phantom mutations from ruining your models.
We want you to step into the mindset of a true ML engineer today, because building models isn't just about importing a library and hitting train.
No, not at all. It is about architectural defense. Understanding how memory is handled under the hood is what saves you from spending 4 days chasing a bug that doesn't actually exist in your math, but rather in your memory management.
Okay, let's unpack this. We know from foundational Python that variables often share references to save overhead.
Right. Python is fundamentally lazy, in a good way.
Yeah, it wants to be efficient. You assign a list to a new variable, and Python just points both variables to the same physical location in memory.
Exactly. It's just two names for the same house.
So when we start building complex ML configuration dictionaries, our instinct is to protect them by creating a copy. But standard copying is, well, it's a completely false sense of security unless you understand what the memory is doing.
The illusion of safety is always more dangerous than knowing your code is vulnerable. Let's look at a standard configuration setup. You have a dictionary called config.
Okay, so a basic Python dict.
Right. Inside it, a learning rate, so all R is 0.01, and a nested list for your hidden layers. Let's say layers points to a list of 64 and 32.
Pretty standard neural net config.
Yep. Assigning this directly to a new variable is bad, so you use Python's built-in copy method, writing shallowconfig.copy.
On the surface, that looks like a responsible engineering decision. I use the word copy.
It does look responsible, but let's look at what the computer's memory allocator actually did, using Python's id function, which returns the exact memory address of an object.
Right, like a serial number for the memory block.
Exactly. If you compare id config with id shallow, they are absolutely different. The outer dictionary wrapper is a brand new object.
Wait, if the outer dictionary is a new object, that implies the copy worked.
It did work for the first layer.
But I'm guessing the trap is sitting inside that nested layer list. If I compare the id of config layers with the id of shallow layers,
they share the exact same memory address. The comparison returns true.
So a shallow copy is like duplicating a filing cabinet, but inside the new folders, you just put sticky notes pointing back to the original document.
Oh, it's a brilliant way to put it.
Thanks. But if my second experiment modifies a document in the new cabinet, I'm actually overwriting the original file in the first cabinet.
What's fascinating here is how that analogy highlights the vulnerability perfectly. The cabinet itself is new, but the heavy data, the nested lists, the data frames, the tensors, they're just pointers.
Which is wild to think about.
It is. So in experiment 2, drops a layer from that list to test a smaller network. It is actively reaching back and rewriting the architecture that experiment 1 is still trying to use.
That is terrifying for reproducibility. If my baseline is changing every time a new experiment spins up, my results are completely invalid.
100% invalid. You're comparing apples to, well, corrupted apples.
So how do we build a completely new filing cabinet with independent copies of every single document inside?
We bring in the copy module and use a method called copy.deepcopy.
DeepCopy.
Yeah. When you pass your configuration into DeepCopy, you are invoking what I like to call the recursive explorer mental model.
The recursive explorer, I love visualizing that. How does it operate differently from a shallow copy?
A shallow copy is it's like a lazy scout. It looks at the top-level container, builds a new one, throws some pointers inside, and clocks out.
Job done, time for lunch.
Exactly. But the recursive explorer actually opens every single container, walks into the dictionary, finds the list. It walks into the list, finds the integers.
It's thorough.
Incredibly thorough. It recursively extracts every nested object and physically rebuilds the entire structure from the ground up in a completely isolated block of memory.
So running that id, check again on the nested layers after a deep copy guarantees a false result.
Absolutely. id config layers is false. They are physically separated.
Which means experiment 10 can dynamically mutate its configuration all night long, and experiment 1 remains isolated and perfectly intact.
Exactly. You are safe.
Here's where it gets really interesting. Because an overwritten config file is annoying, sure, but it's a relatively small piece of data.
Right. A few kilobytes at most.
Exactly. Let's escalate this to the actual heavy lifting of machine learning. Training neural networks takes hours, sometimes weeks, of expensive GPU compute. What happens when this memory sharing trap hits the training loop itself?
Oh, man. You experience the model checkpointing failure. It is an incredibly painful rite of passage for ML engineers.
Set the scene for us. How does this failure actually happen in practice?
Okay, so you are training a deep neural network, evaluating its performance on a validation set after every single epoch.
Standard procedure.
Right. Suddenly, at epoch 50, your validation loss drops to a beautiful record low. You want to save the exact state of your model right then and there.
Because you don't know if it's going to get better or worse from here.
Exactly. So in PyTorch, you might extract the weights using best weights, model.static.
Okay. You grab the current state dictionary, tuck it away in a variable, and let the model keep training for another 50 epochs just to see if it can squeeze out a little more accuracy.
Exactly. The training continues. But, as expected, the model eventually starts memorizing the training data. It overfits, and the validation performance degrades.
Which is fine because we saved the best version at epoch 50, right?
You'd think so. You stop the run, and you go to load your best weights back into the architecture. But the weights is inexplicably mutated.
Wait, what?
Yeah. They are the terrible overfitted weights from epoch 100. The pristine model you found at epoch 50 is permanently overwritten.
Oh, wow. It's like thinking you took a photograph of a winning racehorse crossing the finish line, but because it's a shallow copy, the horse in the photo just keeps running and getting tired.
Yes, exactly. Or it's like a live video feed masquerading as a photograph.
That is just brutal. But we have to ask why the framework designers built it this way. Surely they know this happens.
They absolutely know. PyTorch's stated dict returns references intentionally.
Intentionally. Why would they sabotage us like that?
It's not sabotage, it's survival. If you have a massive language model, your weights might take up 10 gigabytes of VRAM.
Oh, I see where this is going.
Yeah. If PyTorch did a deep copy every time you check the state, you would instantly run out of VRAM and crash the GPU. It passes references to preserve your hardware.
Okay, if it's an intentional design choice to protect my GPU, how do I actually save my checkpoint without blowing up my memory?
You have to explicitly take control. You either wrap that call in copy.deep, model.state.dict, if you actually have the RAM to spare.
Which is rare with big models.
Very rare. So the better option is to bypass active memory entirely and serialize those weights directly to your hard drive using torch.save.
I can see how missing that one nuance could cost an engineering team thousands of dollars in wasted cloud compute.
Oh, easily. It happens every day.
But this raises a broader question. If DeepCopy protects our configs, and it protects our checkpoints when we have the RAM, why isn't it just our default behavior for everything in Python?
Because system design is entirely about balancing trade-offs. The trade-off here is absolute memory safety versus computational complexity. We have to consider how these operations scale.
We're talking about big O notation here, right? O1 versus ON.
Precisely. A shallow copy is an O1 operation. It executes in constant time.
So it's basically instantaneous.
Yes. Creating a new wrapper and a few memory pointers takes a fraction of a millisecond, regardless of whether you have 10 items or 10 million items.
But DeepCopy is different.
Very different. DeepCopy is an ON operation. The recursive explorer scales linearly with the size of your data.
Which means context is everything. Deep copying a 30-line JSON configuration is effectively instant.
Right.
But if I pass a 10-gigabyte pandas data frame containing my entire training corpus into a deep copy function.
Oh boy. The recursive explorer will attempt to visit and duplicate every single cell in that data frame. Your CPU usage will spike to 100%, your memory will instantly double, and the operating system will forcefully kill your program with an out-of-memory error.
It's a kamikaze move.
Completely. You take the whole server down with you.
So if deep copying massive data sets is a kamikaze move, how do we enforce safety in a data pipeline? We can't just leave our data exposed to accidental mutations, right?
No, we pivot to a different architectural pattern entirely. Immutability.
Immutability. Okay, break that down for you.
Instead of creating copies to protect the original data, we fundamentally lock the original data so it cannot be altered by anything. In Python, a brilliant way to achieve this is by using data classes with the frozen parameter. You define your object with @DataClass, frozen true.
So instead of painstakingly recreating every piece of paper by hand to keep it safe,
Which takes forever.
right, immutability is like laminating the original paper so nobody can write on it in the first place.
Exactly. They can read it, but they can't write on it.
But when do we use which? When do we copy and when do we laminate?
Well, let's look at what happens if they try to write on the laminated paper. If a downstream function attempts to alter a frozen data class, Python throws a loud frozen instance error.
So the pipeline just halts.
It halts immediately. And in system engineering, an explicit loud crash is infinitely preferable to a silent mutation that corrupts your data over hours of training.
That makes total sense. You want it to fail fast.
Yes. The foundational engineering insight here is if it cannot mutate, it cannot break.
So the mental model for our listeners,
Yeah.
rely on the recursive explorer, the deep copy, for your lightweight configurations and experiment trackers. But lean into immutability and controlled architecture to protect your heavy data sets.
You've got it. That is the golden rule.
We've laid down some solid ground rules for native Python. But let's be real, modern ML engineers spend most of their time inside complex frameworks.
Oh, absolutely. Native Python is just the glue.
Right. We touched on PyTorch earlier, but libraries like NumPy and scikit-learn must have their own invisible memory rules, right?
Entering those frameworks is like navigating a minefield if you only know standard Python behavior. These libraries are engineered for maximum processing speed, which means they aggressively share memory by default. Let's look at NumPy, the bedrock of Python data science.
Where is the trap hidden in NumPy?
It lies in the critical difference between an explicit copy and a slice. If you have an array at call.copy, NumPy physically allocates a brand new block of memory.
Okay, that seems safe.
It is. But if you use array slicing, say, you extract the first 1,000 rows using bracket notation standard, Python lists would give you a shallow copy. NumPy, however, gives you what is called a view.
A view. So it's literally just a window looking at the exact same data in the original array.
It's a new Python object, yes, but it points to the exact same continuous C-level memory block underneath.
Why does it do that?
Because allocating new memory blocks at the C-level is computationally expensive. NumPy assumes you just want to look at a subset of the data quickly.
So if I slice out a batch of images to normalize their pixel values, thinking I'm working on a temporary subset, I am actively destroying the original pixel values in my master dataset.
Yes, you are actively rewriting the history of your data.
Wow. Okay, if NumPy is doing this just to save CPU cycles, PyTorch must be even more aggressive. You're moving massive matrices across the PCIe bus onto a GPU, and VRAM is incredibly scarce. I'd imagine PyTorch actively fights you if you try to duplicate data.
That is the perfect way to frame it. Tensors share memory by default to avoid suffocating the GPU. If you actually need an independent tensor, standard Python DeepCopy can sometimes detach the tensor from the computational graph.
Oh, which breaks your backpropagation.
Exactly. It ruins the entire training process. So you must use PyTorch's native.clone method to get a true copy that respects the neural network's gradient tracking.
So every framework requires a different dialect. What about scikit-learn?
Scikit-learn is actually a beacon of safety here. It embraces a functional design pattern.
How so?
When you apply a transformation like a standard scalar or a PCA reduction, The framework generally returns a brand new data set, deliberately avoiding in-place modifications to your original arrays.
Which transitions us perfectly to building our own robust pipelines. The source materials highlighted an example called the OS Automator pipeline, specifically contrasting unsafe preprocessing with safe preprocessing.
Yes, this is critical.
How does functional design actually look in code?
It relies on building what we call pure functions. Let's look at an unsafe approach first. You write a pre-processing function that takes in the length of dictionaries, maybe bounding box coordinates for object detection.
Okay, pretty common task.
Right. Inside the function, it loops through and modifies the size value in place. Item size equals 2. Then it returns the list.
The danger there is side effects. Whoever passed that data into the function just had their original variables permanently altered without any warning.
Precisely. A pure function eliminates side effects completely. Inside the safe version, the very first operation is creating an isolated state, usually by deep copying the input data if it's small enough, or returning a newly allocated array.
And then the math happens.
Right. The mutations happen on the isolated state, and that brand new object is returned.
So what does this all mean? The pure function gives us idempotency. What comes in stays untouched. What goes out is a brand new object.
Exactly.
That means if I run a massive data pipeline and it crashes at step 5 out of 10, I don't have to restart the entire pipeline from scratch. My data at step 4 is still pristine because nothing was modified in place.
You maintain a verifiable audit trail. In an unsafe pipeline with in-place mutations, a crash leaves your data in a mangled, half-processed state. Pure functions guarantee that your pipeline is entirely deterministic and reproducible.
Understanding these architectural nuances, the NumPy memory views, PyTorch cloning, pure functional design, this is the dividing line between someone who writes basic scripts and an ML engineer who builds resilient systems.
It really is night and day.
How do we synthesize all of this into a repeatable daily workflow?
Professional ML systems are built on a foundation of structural paranoia.
I love that phrase, structural paranoia.
It's true. You isolate configurations. You aggressively avoid shared state. You enforce immutability wherever the system allows it. To make this actionable, we have a 5-point engineering checklist.
Our listeners should definitely lock this in.
Absolutely. This should be your mandatory pre-flight routine before launching any training job.
Let's run through it. Step 1 is the nesting audit. I'm assuming this means physically checking your data structures for hidden depth.
Yes. Look at your configuration objects. Are there lists inside your dictionaries? Are there dictionaries inside those lists? The moment you see nested depth, a shallow copy becomes an active hazard.
Got it. Step 2 is framework awareness.
Which means context switching based on the library, knowing that NumPy requires .copy to avoid views, and PyTorch requires .clone to maintain the gradient graph.
You can't treat them all like standard Python.
Exactly. Step 3, the identity proof. Never blindly trust that an operation gave you isolated memory. Prove it.
Prove it with code.
Yes, use the id function to verify that the memory addresses of the internested objects are completely different.
Step 4 is the performance check. This is where we respect the big O complexity, asking ourselves, is it safe to unleash the recursive explorer here, or am I about to drop a 50-gigabyte dataset into an ON operation and crash the server?
Crucial step. And finally, step 5, the immutability option. Before you write complex defensive copying logic, ask if the object even needs to change at all.
Right.
Can you just use a frozen data class and laminate the data instead?
I highly encourage our listeners to take this checklist and actually feel the mechanics in their own code editor. We have a micro exercise for you today. Open Python, create a nested configuration dictionary, and intentionally apply a shallow copy.
Yes. Build your mental model by breaking it on purpose. Modify the nested list in your copy, and then print the original configuration. Watch it mutate.
It's infuriating the first time you see it.
It is. Feel the frustration of seeing your data change when you didn't ask it to. Then, implement DeepCopy. Print the memory IDs and verify the isolation. Simulate 3 experiments to ensure they don't interfere.
When you see those id numbers match when they shouldn't, and then you apply the fix and watch them split into completely independent memory addresses, man, that is a profound realization. It makes the invisible architecture of your code totally visible.
If we connect this to the bigger picture, how you manage memory references is not just a syntax detail. It is a fundamental system design decision.
It changes everything. Careless copying leads to shared state, contaminated hyperparameter searches, and systems you fundamentally cannot trust. but right copying.
Leads to reproducible ML.
Exactly. Isolated experiments, deterministic pipelines, and machine learning models that are actually ready for production deployment. You are laying the concrete foundation for reliability.
Now that we've locked down the correctness and isolation of our systems, we have to deal with the consequences of creating all these independent objects.
Oh yeah, the cleanup.
Right, because if you follow these rules, you are going to have a massive amount of data floating around your RAM. In our next lecture, we are moving from correctness to performance as we tackle garbage collection and memory management in ML systems.
It is the unavoidable next step. Once you master creating independent memory safely, you have to master how the Python interpreter cleans it up so your server doesn't catch fire. Before we wrap up, I want to leave you with one final lingering thought to mull over. We've just spent this entire session exploring how every single framework, from raw Python to NumPy to PyTorch, has its own secret, invisible rules for handling memory.
They all play by their own rules.
Exactly. It makes you wonder, how much of machine learning is actually about designing brilliant algorithms, and how much of it is really just mastering the art of managing visible references in the background? Keep that in mind next time your training loop backs up. Thanks for diving deep with us today.